Hi, this video is about standing waves and sound. Standing waves and sound. So first of all, let's remember some of the definitions. If this is the equilibrium of the wave, we know that this is maximum amplitude. And this part, they're called nodes, and those are minimum amplitude. And then this part is antinode. And it always goes nodes, antinodes pattern. And this is zero amplitude at the same time, right? And also this is fundamental, also called first harmonic. This is second harmonic. And this is third harmonic. So this first harmonic, if you call this string L, the length, it is 1/2 lambda, 1/2 wavelength. And then this is 1/2 lambda, and then 1/2 lambda, and then this is also 1/2 lambda, 1/2 lambda, and then 1/2 lambda. So nodes and antinodes are equally spaced and equally spaced. And the distance between nodes and antinodes is 1/2 lambda. Okay, so no, 1/4 lambda, I'm sorry. So if you look at this is node, and then this is antinode, and this is node. Between nodes and nodes, that's gonna be 1/2 lambda, but between nodes and antinodes, it is 1/4 lambda. So this is antinodes. This is the maximum amplitude. So between them, it's gonna be 1/4 lambda. Okay, so first harmonic has only one antinode. So L, the length of the string, is equal to 1/2 lambda. And then second harmonic has two antinodes. So L is equal to 1/2 lambda. So second harmonic has two 1/2 lambda. And then third harmonic has three antinodes, and that is 3 times 1/2 lambda. So the pattern is L is equal n times 1/2 lambda. Or if you solve for lambda, that's going to be 2L over n. So n is number of harmonic. L is the length of the string. And then lambda is the wavelength. Okay? So these are called harmonic wavelength. Okay? So if you remember, we said velocity is equal wavelength times frequency. And if you solve for frequency, frequency is equal velocity over lambda. And if we substitute lambda here, it's going to be 2L over n. And that gives you an equation of n, which is number of harmonic, times v, velocity, over 2L. That's the frequency. So it is more helpful to solve for frequency that generates the standing wave. But the frequency harmonic relationship is frequency and harmonic relationship is F n is equal n times first harmonic frequency. So if you know first harmonic frequency, and if you can find any harmonic frequency, so it is easy. Now I'm going to solve an example. And for this example, we have a string of 12 meters that is produces a standing wave, and it has 5 nodes. And what is the harmonic number is the question. What is the harmonic number? And also, what's the wavelength we're going to find? So because it says there are 5 nodes, I'm going to put 5 points, 3, 4, 5. And then I'll do my best to draw the wave. So one end is like this, and then total is given 12 meters. So just by looking, you can see each one of them is half lambda, and then we just said L is equal n times 1 over 2 lambda. Okay, and then first of all, this is fourth harmonic, right? Because we have 4 antinodes, so it is fourth harmonic. And then because L is 12 meters, we can solve for lambda, and lambda is equal to L over n, and that's going to be 2 times 12 over 4, and that's going to be 6 meters. Okay, so that's our lambda. And then let's solve another simple example, which is we have a string of 10 meters, length 10 meters, and then the mass is 300 grams, and string has a tension of 40 Newton. And the frequency, what is the frequency of standing wave for which the distance between node and antinode, the difference between node and antinode distance is 1 meter. So let's remember again, when you have, this is your node, and that's your antinodes. So this is 1 over 4 lambda, because you need 2 of antinode to make a 1 wavelength. So in that case, we're going to do the same thing again. If 1 over 4 lambda is equal 1 meters, lambda is equal 4 meters. And then we can find the lambda, and we find the number of harmonic. We're going to find, which is the frequency of the forwards. Okay, so the total length is 4 meters, right? And then that lambda is 4 meters. I'm just gonna plug it in 2 times L, which is 10 meters, and then divide by N. So I'm going to find N, 2 times 10 over 4. It's gonna be 5th harmonic. Oops, yeah, you can see it. So I use the same equation again, 2L over N. That's the relationship between length of the string, lambda, and number of harmonics. Now, the next part is the frequency. How can you find the frequency of this wave? First of all, frequency is equal right here. We have frequency is equal number of harmonic times velocity over 2L. So NV over 2L. And we also know that V is equal Ft over density, or we can write Ft over M over L. So I'm just going to plug it in that information here, N times Ft M over L over 2L. Now I know that it is 5th harmonic, and I know that the length of the string is 10 meters. Okay? And then mass was given 300 grams, and Ft was 40 Newton. Okay? So when you plug it in everything, you will find the frequency 9.1 hertz. So 5th harmonic is 9.1 hertz. Okay, so now let's talk about the sound waves. Now, sound waves transmit energy. Okay, so we have intensity, and it is I. And intensity depends on wave's amplitude. Okay, so the greater the amplitude, if amplitude is high, intensity is going to be also high. So that means louder sound. So greater amplitude, greater intensity. Okay, so we have loudness measured in decibel, and this is the abbreviation dB. And we have this kind of complicated equation, 10 log I over I0. So this is our loudness, and that's intensity. And here's the relationship between them. When the difference between the loudness, the decibel, that gives intensity. You multiply intensity by 10. So here's what I mean. Let's say you increase the decibel from 10 decibel to 60 decibel. So you increase 30 decibel, right? So for every 10, you're going to have 10 times bigger intensity because you have 30 decibel bigger. For every 10, you have 10 times bigger. So it's going to be 10 times 10 times 10, 1,000 times bigger intensity, greater intensity you're going to get. Okay? And then let's talk about beats. When the wave interfere constructively, amplitude will increase. So constructive interference will guide to increase in amplitude. So same thing for the distractive interference is decreases the amplitude. Okay, and the sound level when it increases, beat occurs. So sound level increases, and that produces beat. Now, the number of beats per second is known as the beat frequency. Number of beats per second is known as beat frequency. Okay? Now, let's solve one example. So a piano tuner is using a tuning fork to adjust the key, and that plays A note above middle C, which is frequency is 440. So frequency is 440 hertz. And then the tuning fork emits a perfect 440 hertz tone. When the tuning fork and the piano keys struck, beats of frequency is 3 hertz are heard. So that produces 3 hertz. And the first question is, what is the frequency of the piano key? So what is the frequency of the piano key? Of the piano key. Now, because you already have 440, you can have more 3 or less 3, because question doesn't specify either way. So it can be 443 or it can be 437. So it's going to be one of these. So it is known that piano keys frequency is too high, and the second part says if it is too high, it means that frequency is 443 hertz. And the question is, should the piano tuner tighten or loosen the wire inside the piano? So now we have to decide if the tension should go up or down. Now, in the previous example, we said frequency is equal n velocity over 2L. And we also remind that velocity is equal Ft over density. So if you plug that in, you will see that that's going to be n, and then Ft over mu, and then 2L. Now, if the frequency is too high, it means that velocity is too high. It means that tension is too high. So to reduce it, Ft must be reduced. Ft must be reduced. So tension needs to be decreased. Okay? So that's all for now. Thank you.